Just make sure this clicker works. And does this clicker work? Yeah, it does. There's no back button. There it is. Hi. How are you all doing? Can everyone hear me? Hey. Allegedly, I'm using the podium microphone, but I have no idea if it's on. It is. Cool. So I'm Mae. Like Anna said, I'm a new professor at Princeton University. And I'm here today to talk about something that I've done a lot of, which is doing research with undergraduates, both as an undergraduate student and as a graduate student hoping to mentor undergraduate students. So how many folks in this room have done research as an undergraduate or with an undergraduate student? Okay, I'm actually going to invert that. How many folks haven't? Okay. This advice will apply to all of you. Now, for the folks that have, let me just paint a quick picture of my own time getting research and doing research as an undergraduate. I remember on my first project, I would start with a graduate student sending me like a paper or maybe a list of papers, setting up a weekly meeting, and then saying, see you in a week. And I had a pile of papers to read, and I might have had some intermediate goals or deadlines, but they were kind of soft. And the real deadlines were pretty far away. Maybe a term paper at the end of a semester, or even a publication that I was helping with that'll happen at the end of a year or whenever July 7th rolls around that particular year, picking an arbitrary day about nothing in particular. How many of you had an experience like that? How familiar is this story to you guys? Reasonably familiar. I remember as an undergraduate having the distinct impression that research was important, but not really knowing how to fit it into my semester, how to make sure that it got the same kind of priority as my homework did, how to make sure that when I got stuck, I could work through it, and I wasn't just waiting till the day before every weekly meeting to really make progress on my research. But there's something important that I didn't know then, and that I think I know now. And it comes down to changing the way that I think about what the point of doing research as an undergraduate was. It's not just about helping a graduate student or helping a professor work on one particular problem. It's about teaching. It's about learning as an undergraduate what it is to do research. It's about learning as a graduate student what it is to mentor, what it is to explain your research even to someone. It's about teaching what research is through experience. And this metaphor, this idea that this is a teaching exercise, to me also pointed out an implication. That if research over the course of a semester with an undergraduate student might feel more like an exercise in teaching, then maybe we can also think of it in terms that we all have a lot more familiarity with, in terms of a class. So for the rest of this 40-ish minutes, we're going to go through sort of pushing this metaphor to the limits. And I'll show you some examples of how the idea, hello. Of course you may. A student that is not currently enrolled in a PhD program. Any student that is not currently enrolled in a PhD program, in my parlance, is an undergraduate. I'm including master students, even though that's definitely false. Because what I mean to say is that there's a clear divide between the ways that students who are not pursuing a PhD get involved with research versus ways that students who are pursuing a PhD get involved with research. And we're going to talk today about the interface between those two, when someone who is doing a PhD starts working with someone who's not yet doing a PhD. Hopefully that's helpful. I don't actually know what the term for this is in English outside of America. I'd be curious to know later. All right, let's talk a little about classes as a metaphor. So when you're a student and you go to take a class, and we've all taken classes before, what's one of the first things that you interact with, or one of the first things that your professor desperately wishes you would interact with? Well, it's a syllabus. It's a couple of pages that outline what your lectures will be on, when your assignments are due, and what sort of final assessment you might have. And for the purposes of this talk, our final assessment is going to be a final project, since that's closer to the research idea. It's a document, it's a plan. that sets out a desired learning objective and learning outcome, divided into a smaller set of objectives that will cover and teach some skills or knowledge that you want the student to walk away from. And importantly, those objectives, that skills and knowledge, what the class is teaching, is not the final project was done. There's something about it, something about why we're offering this class that's distinct from because there was a project at the end of it. What would the equivalent be in research? Well, the syllabus is a planning document, right? So the equivalent would be whatever your plan is for a semester of research with an undergraduate. Now, viewing a research project as something that has such a plan has a lot of implications about the research projects we do. Implications on how we select them. Implications on how we choose to onboard our students and get them started with projects. And also even implications on how to keep our students motivated throughout the semester. And through all of this, by the way, I say the word plan a lot. I want to just quickly take a step back and say, no plan survives first contact with the students. When I say things like we should build up a plan, we should metaphorize it to a class structure, we should think about a document right at the beginning, I'm not saying that this is a contract and exactly 37% of your grade will be participation. I'm saying that having that level of insight into what you want to do with your semester, whether you're an undergraduate student, having that level of insight into what's expected of you and how to fit this into your classes is useful. And that this exercise is not about having the plan. This exercise is about learning how to do the planning. And ultimately, you'll need to be really flexible as the semester goes on. Okay, disclaimer over. Let's talk about implications on how to select your project when you keep in mind research is teaching, maybe we should have a syllabus. Perhaps the most important part of a successful research effort is selecting an initial project. So what should we look for when selecting a project? Either if we're an undergraduate student looking for our opportunities, or if we're a graduate student looking to recruit researchers. The first, that we can identify an actual semester-sized project out of our huge research project. Honestly, there are a lot of ways to do this, but I find that one of the best ways to do it is to ensure that you have mature research. The more mature your research is, the more likely it is that you can do things like actually predict sub-goals that are likely to be necessary for your research to be successful. You could also have mature frameworks. If you have, say, a semantic framework for building out type systems, a good example of an undergraduate project would be to use that to build something with it. In all these cases, though, you're not just starting out. The most important part is that your project is mature enough that you have a reasonable idea of what done might mean for your undergraduate students. Okay, beyond knowing what a project is, we should know how to measure success on that project. So there needs to be some clear metrics for that success. This sometimes comes in the form of obvious things like finish this proof. But frequently the success that you're looking for with your undergraduate isn't about work done per se, so much as lessons learned. Ooh, can we close that door? Thanks, y'all. This is something that you can do, not close the door, measure success. It's something, it's something that you can do together, collaboratively, that a mentor and mentee can sit down together and really work on and work through. What else do we need? We also need to figure out the tools that are required to achieve success in a particular project. We need to be able to establish what the prerequisites of the project are, which in almost all cases is going to include at least something that's not taught well in a class, or at least something that you're not sure is covered in a class. This exercise is especially important when you're looking to work with faculty. As someone who is a professor at Princeton, I can confidently say that I've never taken a class at Princeton. I don't really know what's in them. I know the ones that are in my discipline maybe, but if I see you've taken data structures, I might incorrectly assume that that means you know how to write a red-black tree in your sleep. And that's not necessarily true of every data structures class. The last thing If the project you're intending to get help with needs to last more than a week or two, it's important to not just say, this is your one project, go, see you in 2 months, but to establish intermediate goals, to break down the project into a series of deadlines that are more tractable and that fit better into the structure of a semester. If you're a student that's looking for a project, the thing you should ask yourself is, how would I break this project down into goals? Do I know what I should have done next week or tomorrow when I work on this project? And let me reiterate for the undergraduates in the room, this isn't necessarily something you're always going to get up front. It is okay, and in fact really necessary, to ask for a lot of this information. It's a really good way to sit down with your professor and mentor or your graduate student helper and start paving the pathway for success in the project for yourself. We are somewhat busy, somewhat scatterbrained people who don't necessarily realize that we never told you that you can't work on this until you've read Tolstoy's War and Peace for some reason. Okay, lot of advice, rapid fire. Let's take a step back and look at some examples that we can hopefully generalize by, because apparently that's good, according to Neil. So I'm going to have 3 examples, and this one particular example will have had 2 tries. So for a while, for a few years, I was working on building out a new type system. Technically speaking, it was a substructural type system that ensures destructive race freedom for concurrent shared memory programs. Much less technically speaking, it was a type system, kind of like the one that you have in Rust, which proves that multi-threaded code is always thread safe, even if you do some mutations. I wanted to take this larger research project and divide it into a couple of undergraduate-sized semester-long projects, say. Let's look at how I succeeded on doing this, focusing on those criteria of seeing if the research was mature enough to yield a project, whether we had an idea of how to measure success on the scale of the undergraduate work, whether we had a sense of what the prerequisites for the project were, and whether the project was divisible into deadlines. Okay, story number 1. The first time I tried working on this was at Cornell University. I was approached by a master's student who wanted to do a master's thesis, and I said, sure, that sounds fun. I'm working on this new type system for concurrency. You can help me with that. The student approached me, and I said yes at a pretty early stage of the research. In particular, I hadn't actually figured out, from a technical angle, how this whole thing would work. I didn't necessarily even know it would be substructural yet. I could have thought of it as any kind of ownership system. What I had was a syntax and a bunch of examples of things that I wanted to make sure worked, and a bunch of examples of things that I wanted to make sure didn't work. As a corollary, I actually didn't really have a notion of what you would need to work on this. I didn't know what the fundamental technology was, and I didn't know how to onboard onto a vague nebulous cloud of the last 25 years of research in uniqueness and ownership. So the project I came up with was to tell the student to just go ahead and build an interpreter for this language. I thought, that'll let us test out my examples. That'll let us see sort of where the syntax that I'd also designed starts falling short, how annoying it is to use this even before we have a type system. Okay, that was the project. What do we think about our criteria? Well, it wasn't great. Because the research was so immature, while I could identify a project, it wasn't really clear how that project connected back to the research. Because it was so early that I didn't know how the type system would work, things like the syntax actually were probably going to change to adapt to the needs of the system, which would cause the overall semester project to drift further and further away from what the research goal wound up being. That in turn made it really hard to measure success on the project. While I guess in some sense you could say if you finish an interpreter, good job, it's not clear what that did to teach the student a lesson. The student had already taken compilers the class, and it's not clear what that did to further research. I also didn't really do a good job of onboarding. There's a book edited by, I think, James Noble and Tobias Rigstad on just here's how you do ownership and uniqueness papers, and that was the resource that I picked, and it was way too much for your first week of reading. The only real saving grace here is that interpreters are great for deadlines. They're a driving structure of a lot of coursework in programming languages, so we tend to kind of know how to divide them into deadlines. Okay, that didn't work. But let's try again. So a year goes by, and I'm now at UC Berkeley, and I'm trying to recruit students again. At this point, I've spent months really working on the type system. It's way later in the project's maturity, and I've gotten to the point where the entire system is written out on paper. I'm pretty confident the rules work. I've even figured out how to divide the correctness questions about the system into a classical framework of progress and preservation and a dynamic semantics I've already written. What has to happen next is those proofs need to be done, which is itself a daunting task. But I had some good starts. I knew what invariants I would need to maintain and what inductive invariants those proofs would probably rely on. And I knew how to divide these proofs into sub-goals and lemmas that honestly seemed like they would really work out. At this point, I could pretty confidently predict how much time it would take me to do this project and how likely it was that each individual theorem statement was actually true in my system. The project here, prove that progress and preservation, chase my lemmas around, see how it goes. How do we measure up now? Well, the project's much later, and because I've got all of these lemmas to chase around already, it's not that hard to see how I could measure success. Each of these lemmas will teach the student both something about how to prove this kind of property in a system, giving them experience in practical usage for programming languages papers, and further the research. It's also fairly clear how the system works. I know at this point what it is as a substructural type system. I know what it's like. I know what it's not like. I know what specific antecedents you need to learn. And in particular, I know which chapter of advanced types and programming languages you should read. Having already divided the proof means that each lemma can have its own deadline. So we had a good structure for running the entire semester. And all of this is really enabled by the fact that the research was more mature, that I had a good idea of where the pieces were and how they would all fit together before I tried to recruit an undergraduate. Okay, that's a good example. Question?
Are these mechanized proofs?
Some of them are. The goal was not to mechanize them for the undergraduate work. The undergraduate about halfway through this project was like, hey, I've heard about this thing called cock. And I was like, I hope I know what you're talking about. And the students said that they wanted to try using that to mechanize the proofs. And I was like, you know what, let's do this thing. And the student got through a bunch of them and decided that was incredibly hard. And we didn't finish mechanizing it. Okay, one more example. This is from when I was an undergraduate student. So when I was an undergraduate student at Brown University, when dinosaurs walked the earth, I was looking for research, and I found that my professor, Sriram Krishnamurthy, and his graduate student, Joe Politz, were trying to recruit students for a new project, which was a tested semantics for Python 3. The idea behind the project is that we would take all of Python 3 and identify a core language that sort of captured the essence of that. We'd build a desugarer, a sort of translator that only works locally, from full Python to this core syntax, and we'd write up formal rules describing the operational semantics of the core language we'd designed. Ultimately, Python has its own test suite, which is very cool. So we could use the tests that Python used to validate its own implementations were real Python to check to make sure our implementation was also real Python. That was the project pitch. And the actual semester scale project for this one was, let's just do the whole thing. Which was a lot, but actually kind of worked out this time. Okay, why was this project a good idea? Well, it turns out that this wasn't the first time Joe and Sriram had done this. With just the PhD students, Joe and Sriram had previously built out a tested semantics for JavaScript, so they kind of knew what the flow of the project should be like. This was their second example of a successful strategy. For it to work, they knew they needed to have a robust and mature test suite along with a good infrastructure for writing the semantics themselves, something that was accessible to the students, which they had. They'd already developed that. The PLT group that Sriram is deeply involved in is very interested in educational tools. They also knew that this was such a big, big chunk that just kind of do all of it was a scary thing to tell the undergraduates, but they had this test suite, which they were able to divide down into different levels of semantic features and even different classes of syntax, which meant that we could use these tests to show the progress of our implementations, which would prevent us from feeling like we were just climbing up a hill that we could never see the top of. Between these tests and the fact that our research was based on interpreters, we actually had a pretty good setup for intermediate deadlines. This satisfies our criteria. While the project was entirely new, the frameworks we were working in were mature. It was basically just a second example of a strategy that had already worked. It was also easy to measure success. We literally had a test suite that could have a percentage of succeeding and failing. Additionally, it wasn't super hard to figure out what the prerequisites were because, well, the previous project. Whatever they needed to make the JavaScript thing work is probably what we would need to make the Python thing work. And like I just said, tests and interpreters are great for deadlines. So example 3, good research project. Let me take a step back, but not literally because the microphone's fixed. What do I want you to take away from these examples? Well, for current undergraduates, or really for anyone else who's looking to get involved with research, this is really about what to look for when you're selecting your projects, how to know what your project expects, and to know what's expected of you. And this is going to be a repeating theme. It's a call to talk to your research mentor, even if it's a professor, perhaps especially if it's a professor, to figure out what these things are, to figure out how success will be measured for you, to figure out what your deadlines are. If you don't know this information, that's fine. But if you learn it, you will probably have an easier time navigating your semester. Meanwhile, if you're one of the current graduate students, I hope this guide can help you decide not just which projects are excellent for undergraduate students in general, but also when your project might be ideal for an undergraduate researcher. Not all your projects are at all stages, and that's okay. If you feel like you're waking up in the morning and you just want to work with an undergrad, use that as motivation to get your project a little further along, to sort of build out, ask yourself, like, what are the 4 things here? What is this mature? How would I measure success? What are the prerequisites? What is this semester-sized project? And use that to motivate yourself to get to a point where you can get your undergraduate help. Ideally before you start soliciting for undergraduate researchers, which, let me tell you, is a lesson that we tend to all learn too late. So my apologies to anyone in the room who's had a first research assistant experience. All right, let's go back to our syllabus. I've just prattled on for like a solid 20 minutes about how to select a final project for your work. But I said syllabus in class, right? There's other things here beyond just that final project. Now we need to go fill in the rest. Everything that leads up to our final project part of the semester. In particular, we should talk about how it starts. Where are we going to start? Well, you start wherever the students are. If a student comes to you doing research, they've got some background, and that is where you start your syllabus. And where do you want to get? Where the project is. You've done all this work to identify prerequisites. This gives you the skeleton of your curriculum. Your job now is to find a pathway that can bridge the gap from where the students come to you to where the students start. Your job is also to accept that there's going to be something there, that there will be some more onboarding than just read this specific draft of this specific paper. Let's look at some examples. So, in the project I did with Fearless Concurrency at Berkeley the first time, my student came in with a great degree of mathematical maturity. Where did my student need to get? Proving progress and preservation. Now, a great degree of mathematical maturity is excellent, but my student also didn't come in with any programming languages knowledge, or really computer science knowledge. My student was a math major. So what's the pathway that takes us from mathematical maturity to proving progress and preservation? Well, it's about a semester and a half of programming languages courses. This is a big lift. And I honestly thought that the student probably would just leave and not be able to do it. But rather than just say, I'm sorry you don't have the background, I took my time, I sat back, and I figured out how to create sort of week by week chunks of excerpts from types in programming languages that would teach what you needed to know to even understand that progress and preservation was something worth proving. And this took me a few hours, not super long. I mean, Benjamin Pierce is a brilliant writer and he does great course design. So I sent this over to the student and I was like, hey, this is probably too much. Here's the amount of work that would need to happen before you can start. And that student said, okay. And then 2 weeks later, that student came back and said, I'm done. And I said, okay. And we were able to get started. And that was truly shocking. And I say it not because you should only work with those students, but as an example that even if a student seems like they're a little bit far from what you need them to be, it's sometimes worth it to give them that chance to catch up. Okay, let's look at another example. This one is a pretty cool onboarding story. When I was working on Python when I was an undergraduate with Joe and Triram. Joe and Triram were also slated to be the professor and TA for the standard undergraduate programming languages course that fall. So what they cleverly decided to do was integrate all of the prerequisite knowledge that someone who just had I can program in Python and I've heard of data structures before would need to go from there to I'm writing a course semantics. And they sprinkled it throughout the semester. They built literal classes and literal class projects around it. The final project of this class was the onboarding project for the research. We were supposed to take everything we learned about how to write operational semantics and then define an operational semantics and an interpreter for a language that looked suspiciously like a core Python. Which of course dovetails really nicely into a research project that is a formal semantics for Python 3. The real secret sauce connection that made this possible was the existence of PLT Redux, which is a brilliant tool that allows you to write semantics in an interpreter-y way, and more importantly, run your semantics against tests later. Okay, well, building things into a core class is a pretty out-of-reach thing for most of us, but you can do this sort of build-a-class mentality in general. Here's the third example. This is in distributed systems, so consequently, I will say nothing about the research. This distributed systems project, we decided to advertise for undergraduate researchers one semester, and we wound up getting 40 interested undergraduate research assistants, all of whom had about the same combination of classes and previous experiences. It turns out that 40 undergraduate research assistants is too many undergraduate research assistants for, I would assume, anyone. But rather than tell them, no, I'm sorry, this doesn't work out, we decided to just kind of onboard them all. We sat down, we figured out what you need to do to get from the end of a class in our standard curriculum to the beginning of this project. And we built out, a couple of lectures and a couple of deadlines and basically ran an actual course on the margins of our semester in order to take these students to preparedness. We figured that beyond just teaching them the skills they need for the project, it'll show them the specifics of we're going to use RDMA and C++ style things and let them decide for themselves whether that was well beyond the pale or not. After this semester of the literal class, 15 wound up continuing on to do research with us, which, pro tip, is still too many. But there were 4 graduate students involved in the project. So we each took on about 3 to 4. They worked in teams. That was how we ran the semester anyway, and it worked out for us. So what do I want you to take away from these examples? I don't want you to see these examples and walk away from this thinking, my God, I'll never manage that. It's so much work. I have to write an entire course curriculum to work with one undergraduate. And similarly, as an undergrad, I don't want you to walk away thinking, I don't want to start research after I have to take an entire course. I want to start research today. These examples were very much outliers. Rather, the takeaways that I'm hoping we get out is that it's if you're an undergraduate, it's completely okay to see a research project that might excite you or might entice you and realize that you're not quite ready for it, that there's something more that you have to learn before you can really get started. that you open up a file and you see a squiggly little symbol and you're like, well, that's not good. The important thing, rather, is to be honest about your preparation and to be honest about your motivation. Tell your research mentor, I don't recognize these symbols, but I love this problem. And avoid the common pitfalls of either the fake it till you make it, of course I've done category theory, just assuming you can pick it up in the margins. Or on the other side, the fail early, fail often mentality of, I don't recognize one of these 370 pages, so I will not do this research. Let it be your research mentor's job to figure out if there is a good pathway for you from where you are to the research start that makes sense for the project. Don't ever say no to yourself. Meanwhile, other hat, if you're a project mentor, if you're a graduate student looking to work with undergraduates, just remember that the students who are joining your projects are not you. They will not have exactly your background. They especially will not have the background that you pretend to remember that you had when you think you're about their age. And they won't necessarily have a clear picture even of what their background is. They won't know whether they're good or bad at something so much as whether their class was easy or hard when they were taught it. And that's okay. If you have the time in your semester to put in the work to figure out what they are bringing to the table, what you need, and sort of build out that pathway between the two, even if it means building out homeworks or picking a textbook to select from, then you can get really rewarding experiences even with undergraduates that seemed initially ill-prepared. Conversely, if you just say yes and you don't do any of this, you're really setting yourself up for an undergraduate that ghosts you. Someone who's not ready for the research and doesn't know how to get ready for the research kind of definitionally can't do it. Okay. Let's return to that metaphor that we were using to drive the whole thing. The metaphor of a syllabus or a class for research. We've seen a final project, and we've talked about how to pick it based on our mature research. We've talked about the established prerequisites and how that we can use those plus knowledge of where our students come from to sort of bootstrap a pathway that takes our students from where they are to where they need to be. Now let's see how we can take advantage of how the fact that our project was easily divided into deadlines can mean that our semester keeps motivation up. Now, in the metaphor of the syllabus, when you have a final project and it's divided into deadlines, it's usually not the case that you are doing your classes and you're doing your homework, and you're doing classes and you're doing your homework, and then there's a sudden discontinuity where everything stops. And now every week you have a final project due and there's nothing else. I mean, maybe if it's like the last 2 weeks of term, that'll happen, but if it's a month or 2 month long project, that's really not how we structure it. Rather, we interleave it. The first deliverable or two of the final project will happen sometimes during homeworks, at the very least while lectures are still going on. What that suggests to me is that we should take the same approach we took to the semester's final project to each of these individual sub-projects. We should take each individual sub-deadline and ask ourselves, what's the objective here? How do I measure success here? What are the prerequisites here? Which will allow us to intersperse the work on our actual research with the work on the sort of learning how to do the research, with the prerequisite work. This is essential for maintaining motivation. No matter how motivated a student is, telling them they have 3 months of textbook work to do before they're allowed to talk to you is a real blow. Telling them they have 2 weeks of it before they can start reading your papers, and then another week or two before they can start building an implementation is way easier. I kind of said this, but basically, you want a gradual transition from the onboarding to project, because your project, which is enabled by your project being made from small deliverables. Okay. Good goal. Let's see it in action again. So what were the small deliverables that we could interleave for the Fearless Concurrency project? Well, step number 1 on proving progress and preservation for a type system. Read the type system. And you really should break it out at this fine granularity. Because step 2 isn't write progress and preservation. Step 2 is understand. So what I did with this is I had my student go through my rules portion at a time and explain those rules back to me, what they were there for, what they were in service of. Things like, this is just the normal rule for looking up a variable in a context. Or things like, There's a context split here because we don't want to accidentally reuse the same bindings on the argument side and on the function lookup side of this application. This is important not just for the purpose of teaching the student, this is sort of also part of the onboarding, but also for the rules themselves. Because as the student presented a kind of overcomplicated or missing the point explanation, sometimes it meant that, well, that was an overcomplicated or missing the point rule. So we could use this interactive process to refine the rules down to a simpler core that still captured what we needed them to capture. Once both their students' understanding of the project and the rules themselves are stabilized, time to formalize some invariants, some things that make the context sane, the actual shape the heap needs to be if the heap is going to support data race freedom. Now, I actually did this part ahead of time, because otherwise I wouldn't have any idea how to structure the proofs. But I didn't show that to my student. I still asked my student to dream up invariants on their own, sort of as a sanity check, since I didn't have the proofs. If the student wound up with different invariants from me, that could be an indication that my invariants weren't going to work. Conversely, if the student had the same invariants from me, that's great. It's a strong indication that probably this is actually what makes the system work out. In this case, my student had the same invariants. Good. After that, we're off to the races. Each individual lemma can be its own subgoal. Eventually, you'll get to full proofs. Lots and lots of small deadlines just for proof, progress, and preservation as one task. Okay, when I was an undergraduate, what were the subgoals for the Python semantics just defined semantics? This one was also done very cleverly. Rather than have just surface Python, core Python, semantics, translation, we defined a lot of intermediate languages. And each time we defined a single intermediate language, we had to ask ourselves, what's the semantics of this particular intermediate language? Do we believe that this is just a desugaring from the language above? I know we eliminated arrays and replaced it with dictionaries in the sky, but did we miss something crucial that should have been preserved in the core calculus? As we assessed whether those were simple or correct, that would wind up, sometimes we'd fail. Sometimes actually that wasn't really simple or that wasn't really correct, and we have to rethink our rules or rethink the way we built our intermediate language. Once we're pretty convinced of that, we have to implement it, build out a desugarer, and then we have to run tests. Because if our desugarer was wrong, then that probably means our intermediate language was wrong, which means we have to go back to coding the rules and do that in a loop for a while. And there were 6 undergraduate students on this project. 3 undergraduate students and 3 other. I think a couple were like senior programmers at a company. I'm sorry, I was an undergraduate a long time ago. So there were but the point is there was a lot of manpower on this task. But eventually we'd converge. We finally got low enough that we still looked like recognizable Python, but we had simple semantic rules for it. And going any lower seemed like it would really eliminate something critical to being Python. So we had our full semantics, and we were ready to test it and publish it. Okay, one last example. The Derasure project, the distributed systems project, how do we break that into deadlines? Well, the project was to build a memory allocator for a distributed system. So first off, rather than have the students jump directly into like a 100,000 line C++ 2014/17 code base, which I don't know if you guys sound really excited about that, but I wasn't. We built them out a private little space where they could build and test their designs for allocators and make sure that they were performant and correct without sort of dealing with the crazy build toolchain. After we managed to do that, we didn't go and integrate it. We wrote documentation about it. We explained the design of these individual allocator as though that was the whole project, talked about it with the rest of the team, talked to the other graduate students, and only then integrated it into the main system, the first time we touched the main code base. So what am I trying to teach with these examples? If you're an undergraduate, it means asking for deadlines at whatever rate you need to be successful. It means if you see something that seems like too big a lift, then maybe it is, and that's fine. It means talking to your graduate student when that happens, or talking to your professor when that happens, and trying to get that broken down, not just assuming if you can't see the next step, clearly it's your problem. Meanwhile, for graduate students, it means basically exactly the same thing. You should really know what it is your undergraduates are working on. And I don't just mean they're working on the Python interpreter. I mean, they're implementing desugaring phase 2.c, and the hard part will be this. You should know how they should break that down. What is a task they could do in the next 4 hours? And if you don't know that, and if you can't figure it out while sitting down and thinking hard about it, you know more about your project than they do. So that certainly means that they're getting set up for being stuck. That is a time to call your undergraduate student right now and be like, hey, let's set a meeting, let's figure out how to divide this goal. Now, sometimes you'll work with undergraduate students who are distinctly smarter than you. I've definitely done that before. So it's totally possible that you'll have that meeting and the undergrad will be like, yeah, obviously the correct way to do this is to points to vague a junction on the board to a category you've never heard of. And you'll be like, awesome, those were words. And and you can let them run, that's totally fine, but generally don't assume they know more than you. Sometimes they do, let it be a nice surprise. Okay, that's enough examples for this one. Let's return again to building this syllabus. We had a final project, we divided it into sub-deadlines, we interleaved those through the semester while we also worked on an onboarding that was more extensive than just reading a paper, but consisted of teaching what you need to know to start a project. The last thing we're going to need to do is measure success. Now, I'm running short on time, so I will say this very briefly, but I want to return to the opening point, that the research experience with an undergraduate student, honestly, the research experience in general until like you're going on the faculty job market, is a teaching or learning experience. It is not about getting the research done or publishing the paper. It's about staying engaged. It's about making progress. It's about learning more about the problem. Okay, disclaimer done. I've set up all these projects. I should tell you how they turned out. So let's measure success for the Fearless Concurrency type system project. The first time. This is the one where I kind of just told someone to build an interpreter and didn't even know why that would be useful. Surprising no one, this project didn't really have a good way to measure success and didn't succeed. And that's because as the research drifted further and further from the project I had assigned, I could spend less and less time explaining to my student why they might do something. I couldn't anticipate problems they'd run into because they were working on a completely different artifact by the end. Ultimately, that left the student adrift, with no research goal to motivate them, and with no research mentor to create sub-deadlines for them. They just kind of disappeared throughout the semester. I wish I hadn't done it, and I'm sorry to that student. But, you know, cautionary tales. It went better at Berkeley. This project, luckily enough, worked exactly as expected. Our deadlines came in rapidly, the students stayed incredibly motivated and engaged. We got really lucky in that the invariants that we wrote matched, and the proofs and lemmas that I set up at the beginning were roughly what you should have proven for our results to hold. It wasn't just like turn a crank and it all goes through. There was serious creativity, and indeed my student found some bugs in the system that required us to redesign a couple of rules. But ultimately, it did fit in the semester I had hoped. And that student has gone on to do a lot of successful research as a grad student, PhD student today. Meanwhile, when I was an undergrad for the Python semantics, was this project successful? Sort of. We published the paper, so I would say also a success. But it was a much rougher one. It turns out that saying, design is semantics, kids, to a bunch of 19-year-olds who had never done programming languages before, will get you some really weird semantics. We didn't exactly have the equipment we needed to make the value judgments about whether each step of desugaring made sense. But we stayed motivated, we stayed engaged, we always knew what the next step was. And because our graduate students stayed on top of us, because they knew what we should be working on, weird things like, hey guys, you just completely desugared away Python scoping issues, were caught early, and were caught often. And it allowed us to really actually have a successful project, even though we were a little bit meandering in the woods for some of it. Ultimately, did the students go on to have success? I mean, I became a professor. The other undergraduate student is I think, lecturer at Northeastern now, and the third undergraduate student is a PhD student. So I'm going to call that a successful research project for the students. Also, the weird curveballs we kept throwing turned out to make the research way more publishable. Python scope is really messed up. Meanwhile, Duratio. This is an example of a project that didn't work for the research, but did work for the students. I designed a complex allocator that I thought would work really well for our distributed domain, and it didn't. And it didn't for reasons that were surprising, assumptions that we thought we could make about the hardware that turned out not to hold. But the students stayed on top of it. The students built out the design basically to spec. The students innovated, found ways around our problems, pointed out when we actually hit a fundamental error that we hit a fundamental error. So, successful research project. What's the takeaway lesson here? Success is not about publishing. Success is about engagement. Success is about learning. Success is about discovering something in your research. If you are an engaged undergraduate student that keeps surprising your research mentor and doesn't publish a paper, you're getting an excellent rec letter out of that. And that's going to matter more for getting into grad school anyway. Okay, well, I'm over time, so I think it's time to wrap up. Let's just say, ooh, someone said something.
No, go ahead, wrap up.
Okay. Let's just say that this metaphor is only a metaphor. And I want to return to my first point, which is that no plan will survive first contact with your research students. Everything changes all the time. There will be a bug and it's critical, and suddenly your project is no longer implement the interpreter, it's go back and rethink the semantics. The point of thinking about this, the point of building out this plan, thinking about prerequisites, interleaving small deadlines, is not to create a contract. It's about the planning. It's about making sure that you have a good answer for what a research project is, because that's the recipe for success when working with especially early stage researchers. Just be flexible. And now I'll take questions.
Time for a question or two.
Hi, Mae, great talk, thank you.
Thank you.
I wanted to ask, in terms of measuring success.
Sure.
Because one of the things that no matter how mature the research project is, it's still a research project. So there is the possibility that it crumbles into dust while the undergrad is trying to get a project out of this.
Right.
How do you then lead them into success and measure the work that they've done when their foundation has gone?
So there's sort of two options here. One is it crumbles into dust and the student's work is instrumental in crumbling it. That's great. That is success. You've just measured it. Congratulations, student. You get an A+. Also, I'm sad. There's the other sadder option, which is your student is working on an example of a type theory and you prove it's unsound 2 weeks in. And now there's clearly no point in that student continuing with that example. Honestly, change the project. Go back, say, hey, we've learned a lot here. You built some skills on how to build out type theory, but we can no longer use this example because we no longer have it. And if you don't have anything else to do research with for that semester, find a way to do right by that student, even if it means converting to a more class-like, here, instead of doing research on my system, we'll do a system that's more stable, a system that's been published, that we know is sound, and build examples there. And ideally, you'll have a project that's a little further on and doesn't crumble. You can get really unlucky and just every 2 weeks your system crumbles, but at that point, you've got probably many concerns that are different than your undergraduate's research success. But yeah, I guess flight to stability tends to be my reaction there.
Thank you. That was very interesting to hear your perspective on both as mentee and mentor in these projects. I did have a question, which was, I've had some experience with doing tutorial teaching, class teaching, where, at least in the system I'm from, you have the distinct advantage that your only purpose is to help the student learn. You have no role in the assessment of the student. It seems with research projects, kind of inherently, you will have to be involved in some way with assessing the outcome of that, even if nominally there are independent assessors, your kind of report will form part of that. How do you kind of balance the kind of joint obligations to making sure they're learning, but also having an assessor hat on at the same time?
I don't have an assessor hat, is the short answer. My primary way of measuring success on research is measuring engagement. It's already so hard to make progress on these things that a failed student, in my experience, is a student who just kind of vanishes over the course of the semester, and that a student who sticks with it and demonstrates success and gets to the end of the semester having learned something useful about research, getting distinctly from where they were at the beginning to where they are now, even if it was not successful in your project at all. I tend to see that as kind of an A student. I'm also from America, the land of great inflation. So it's fairly usual for like us to take undergraduate research assistants and just kind of slap A's on 2/3 of them. We could go deep into debates about what the point of grades are and whether this is a like moral and ethical philosophy or not, but I get to use that to avoid these deep assessment questions when I work with these undergraduate students. And that's been very good for me. The other short and pithy answer is if you're a grad student, which I think most people in the audience are, you have a professor you're working for whose job it is to do that for you. Just make sure you're communicating with that professor enough so that they have the information to make that decision.
All right, let's thank Mae again.